So thanks, Simon. Thank you very much for the invitation. This is an enjoyable meeting with all kinds of various interesting topics. So I'm going to be talking about spectral solvers, and at somewhere in the middle of my talk, there's going to be something not about inverse problems, which is the main subject of this workshop, but about inverse design, which is the same thing, only that instead of recovering something that you want to observe, you essentially try to find a device that performs a certain objective that you want to achieve. So it's essentially the same thing, but people call it, in the photonics area, call it inverse design. But there's going to be also solvers and various kinds of things, time domain and frequency domain. So these are the topics. I'm going to talk about some frequency domain accelerated solvers, and they're accelerated, the integral equation based and green functions and these kinds of things that people have been talking about. And they're accelerated by means of fast Fourier transforms. And they have the kinds of the challenges that were described in the previous talk. So they have some good properties and they can do good things with them. But at some point, when you want to solve sufficiently large problems involving many thousands of processors, those begin to become problematic. And but anyway, based on frequency domain solvers, we have these time domain solvers that are based on frequency domain solvers, and that's going to be the second part of the talk. And the third part of the talk is meant to address this issue that comes up in the other two parts, where you have massive amounts of frequency domain problems that you want to solve, and you would like to do them very efficiently, and the fast Fourier transform becomes a problem. So if time permitting, I'll talk about this novel frequency domain acceleration that doesn't require use of FFTs in any way. So it's really nice to be able to talk to an audience that will just know from the cuff what this means, right? So I'm going to be looking at time domain problems and frequency domain problems that look like that. I hope you can see my mouse. And for the wave equation or for the Maxwell equations, and here are the frequency domain versions of them. And so here, just as a brief mention, I'll mention the green function versions of these problems, where, for example, in the acoustic case, you have the green function, which could be either the Hankel function or this exponential green function in 3 dimensions. And so the simplest possible way in which you can imagine solving the problem of scattering by a surface would be to use a single layer potential on that surface and to seek a solution in that form. And then in order to actually find the solution, you have to solve this integral equation. So basically you represent the field using the green function, and then that is certainly a solution. It's a scattering solution. It satisfies the Silver-Mueller radiation condition at infinity. And so the only thing that is left to satisfy is the boundary condition, and that boundary condition is a boundary integral equation on the boundary. So you're looking for this current mu defined on the boundary, so that when you plug it in here, you satisfy this integral equation. So this is the simplest integral equation. It's not uniquely solvable in many frequencies. And so these things can be fixed, and you can get this combined field integral equations, which is what we actually use. We don't use this one. I've just showed this one just for reference, for simplicity. But there's various kinds of electromagnetic integral equations and ways to get small numbers of iterations in iterative solvers, and so forth. And we're going to use the best one of those. And so that is something that I'm not going to be talking about, because that would be a subject of a different talk. But we do have and use electromagnetic integral equations, for example, that require small numbers of iterations in iterative solvers. So the problem becomes that you have this, if I go back again for a second here, the green function is a singular function. I have to compute these integrals over the boundary of the scatterer in an iterative solver. So given a mu, I have to compute the integral and then iterate in some kind of iterative solver such as GMRes. And so I iterate with that. And so what I have to do then is essentially to compute effectively an integral of this form. And an integral of that form as fast as possible, but it's a singular integrand, and this is a well-known difficult problem. It's a challenging problem. And we've come up with a solution that we're quite proud of. So basically what it is the fact that the recognition that in this integral, the density here is not singular, whereas singular is the green function. The density can have singularities at edges, and those can be addressed too, and I'll show you the how. But the main thing is that this green function is singular all over the place. So this point R has to be observed all over the surface. And so that gives rise to singularities all over the place, but mu isn't, right? So you could discretize differently the mu and the g. The g is known in closed form, so we don't need that's not something we have to find, but the mu isn't. So this is something that we have to represent in some way, and that's what is expensive to represent. And so the way we do it is we use patches that we assume they are square patches in the domain. Here I have a sphere, and so they are logically quadrilateral. Okay, they're of course not quadrilaterals, but they're logically quadrilateral. They have 4 curved sides to them, and then they have some sort of a shape. And then on each one of these things, via parametrization, we use Chebyshev pseudospectral Chebyshev discretizations. And so we have our density discretized in terms of that spectral discretization. And then when we have to integrate, that discretization is not enough to obtain integrals because of the singularity of the green function. But then we go in there and we use changes of variables. If you remember the presentation from yesterday on meteorological data assimilation by Chris Budd, so these changes of variables are analogous to that. So in his presentation, he had these inversions where there was some change of variables that gave rise to resolution of the inversion, higher resolution of the inversion. Here we also have higher resolution of the singularity of the green function by using changes of variables. The changes of variables are explicit. In our case, we use polynomial changes of variables that give rise to refinements that are like this. And then from the underlying mesh, which is a Chebyshev mesh, we interpolate onto these values here, and we compute these integrals. And this is done just once. I mean, I said interpolate, but really this is done only once per Chebyshev polynomial. So this is the pre-computation that is not an expensive pre-computation, and we do that all over the domain. It's a linear cost operation because this only has to be done on the patches that contain the singularities and nearby patches. And so it's a linear time simulation, and it can be very effective. So this is something that we've been using at sort of a business kind of model in a small company for a few years. We eventually published that, and there's a patent on this. Eventually published that last year in JCP. And here you can see simulations for simple scatterers such as a cube with edges. We have some also refinements towards the edges to resolve the singularities of the edges. And that can give you high order accuracy for problems that have edges and corners, open surfaces like a disk, and so forth. So highly accurate results. This is also accelerated using fast Fourier transforms by taking a general scatterer like this and using a Cartesian mesh, of equivalent sources. And the equivalent sources are located on a Cartesian mesh, and therefore they can perform the convolution, which is really what this integral here is, right? It's essentially a convolution, only that on a curved domain, so FFTs are not applicable there, but we rectify that by using equivalent sources, and that rectification has exponentially high accuracy. It's something like it's 1 box away from the domain where this region is. Just 1 box away, the representation by equivalent sources is exponentially accurate. And by doing all of that, we have this high order convergence and for domains that can be quite general. And the thing is that they can be applied, this method can be applied to general configurations because CAD files can be processed. So this thing, as you must have noticed, requires a parametrization of my surface. And so CAD files are precisely that. When you have a CAD file like this one of an object, what you get is a patch and an explicit function, a nerve, a non-uniform rational B-spline, splines basically, a little bit more complicated. And so that is the way that AutoCAD and CATIA and all the major surface representation software works. And so we decided to exploit that, and we developed our own in-house reader for CAD files. And so you take, the problem is though that generally patches are not logical quadrilaterals. They don't have 4 sides to them, right? So there are things that could be like this. And so we developed software that partitions that into logical quadrilaterals. And this could be a talk in itself, and I'm not going to be going into detail, but basically something that looks like that is partitioned into things that are logical quadrilaterals, like so. And then when you look at it in the actual physical domain, they look like this. And so to this thing, you can apply the methods to each one of these patches individually in the way that I described before, representing the unknown surface densities by Chebyshev expansions, and then doing the refinements. It's all automated, and so it works well. So let me show you some examples. In that thing that I just showed you, this would be the surface currents. And once you have the surface currents to compute the near fields and far field, reduces to a problem of integration, which is not challenging. And so so I have a few others. The thing is general. It can have very complicated geometries. Because, as I said, this is the CAD. You take the CAD file, and then you look at each of these patches, and then you split it into logical quadrilaterals, and then you apply the method, and that's it. It's a generic thing. There is no complexity. Here's a submarine in acoustics, and you can see the level of complexity of that mesh here, for example, and every detail here is taken into account, and you have your scattering by doing this accelerated using the FFT method that I described before. Okay, so these are problems that that we've been working on for a few years, as I mentioned. But more recently, we started working on problems that are related to a joint to inverse design and require use of a joint optimization. So in this group, a joint optimization is very well known. We developed that in the context of integral equations, and we use this optimize and then discretize approach. So we had these joint integral equations. And so because they are joint integral equations in the continuous level, we can discretize them in exactly the same way that we discretize the direct integral equations. So we don't need to form a matrix and transpose it to get the adjoint. We just transpose the integral equations, and we discretize that by using exactly the same methods that I described before. And so I don't need to go into the adjoint method. Basically, you have to get something that cancels this blue term here. And so you solve a direct solve and then an adjoint solve, and that does it. And so this is exactly the same as in other areas in problems in inverse design. So I'll show you a few examples here of this optimization method. Here I'm trying to solve a problem where I have a splitting grating coupler. It looks something like this. There's various layers of this thing. There's air here on top, or another layer of glass, and then various silicon and silicon dioxide, and then several layers. And here on this top layer, we're going to carve some shape that looks like that. And so we carve that shape, and that's what we need to optimize. How to optimize that shape in such a way that in this case there's multiple heights here. In other cases there aren't multiple heights, and so we want to optimize that shape in this particular case so that when we illuminate it vertically down, right? So the light gets coupled either to the right of the waveguide. It goes either to the right as it does here, or it goes to the left, and that depends on the wavelength. If you go at lambda equals 1.55 microns, then the light will go to the left. And if you do it at 1.3 microns, the light will go to the right. And the way we do this is by gradient descents. We use the box BFGS gradient Newton method. And so we obtain these things. They get discretized in this particular way, and this device was actually manufactured and tested, and so we predicted this efficiency that 42% of the light will go to the right at the right frequency, and 42% will go to the left at the right frequency. It's a challenging problem because the incidence is normal. Typically, people try to avoid that and go at an angle, and it's easier to do it at an angle numerically. But the thing is that the most relevant configuration is when you go orthogonally to it. And so, so anyway, so this is the actual three-dimensional rendering of it, and this is the fabricated device, and this is the tested device. And you see that in fact, when you go at the right frequency, the thing goes to the left and not to the right, and vice versa for the other frequency, it goes to the right and not to the left. And so here is the coupled efficiency as you depart from that frequency a little bit. So this is the multiplexer, and so you can combine signals, and then at the point of observation point, you can decouple them in this particular way. And so so it has, I'm told by this experimentalist that it has some of the best, by far, absolute insertion losses and isolation. So that means you know, that what is the signal that you get versus the signals that you don't want to get, which is the signal that goes in the wrong direction. There is this manuscript submitted on this particular experimental work, and we'll see what happens. So here is a nice picture of it, and so you do see that the light goes. This is a fabricated device, and so I mean the simulation for the actual fabricated device. And so you see that the light does go down to the right at the right frequency. Here you see it in the real part of it, and very little of it goes to the left, and so forth. One thing that I would like to mention is that this waveguide is infinite to the left and to the right, and so this is a termination problem with an integral equation. It was a problem that was previously hadn't been effectively dealt with. And we do that by using this thing called the window green function. It uses a taper function similar to the one that the previous speaker discussed. And we have plenty of these things. And so I would like to discuss this with Jerry Jarrus afterwards. We have things with fast Fourier transform that very similar to what was described before, and for volumetric problems. And so here we use it in the integral equation case, and it was very effective. There is no reflection. This is spectrally accurate, and that truncation is spectrally accurate. Is a beautiful thing, and you just don't have to do anything. You just write the integral equation over the infinite surface, and then you window the integral operator, but not the identity part in the Fredholm integral equation, and that's it. And it works wonderfully, and it converges very rapidly. If you care about that, here is the initial references, and then we've used it multiple times in various applications. You can do it in 3 dimensions as well, and you have waveguides that are terminated by the window green function. It doesn't have to be straight or anything. It can be any complicated thing, and then as long as you have one or more waveguides going out of it, you just window the integral operator, and that works perfectly. Here there is a waveguide paper that we designed following ideas by this reference, Jablonovich. So the thing is that we only discretize the boundaries versus here where the full domain is discretized by using FDTD. And so because we only discretize the boundary, that has multiple advantages. On one hand, it's faster. But on the other hand, the thing is that you don't have to respect any meshes. I mean, you can discretize and model the inverse problem on the shape of this domain by using splines, for example. And then you change those splines, but the integral equations don't change very much. Okay, when you move the spline, all that does is that the Jacobian in the integral changes, but that's very easy to do. And so that's effective. So in all, in a 15-minute single core run, we obtained 99% efficiency. Jablonovich also got 99% efficiency, but he took an equivalent 35.7-hour run. So it is significantly faster to do this optimization. And this is much smoother than what they got. So perhaps there is some advantage to be gotten there. So here is an optical splitter. So you have an incident wave here that is, we wanted to split it into two pieces, and you would say, well, I could take this pitchfork here and see if that works, and it doesn't, because you want to have all this light come here and be split into one that goes here and one that goes there. So let's do the optimization right now. And so this is a movie, of course. And so, but this runs super fast. I don't have the time right here, but this runs super fast. And you see that in a few iterations of the Newton method, this converges to something that is pretty dark here. And actually 99% of the energy goes into the two different waveguides. So here is the time domain version of it, if you care. So this shape that was optimized somehow manages to split the light into the two signals, and almost nothing, less than 1% goes into the middle. It doesn't have to be 50-50, it can be anything you want, and then the domains look ugly, but you can still fabricate them, so that's not a problem. And so you can do it in any ratio you want, and that works. So this is also a fabricated domain. It hasn't been tested yet. And so in all cases, we have 99% efficiency, just like the Jablonowicz this, and so same efficiency. I'm repeating here, so apologies for that. So here are other types of optimization problems. So these are particles. And so in this is a toy problem, two-dimensional problem, building up to something that I want to show you a little bit later. And so we're going to have these elliptical domains all over in this rectangular region. And these are going to be particles of silicon in air in this particular case. And so we're going to be illuminated this with a plane wave, and we want to design this ellipses. These are all ellipses, and we have to take the radii of the ellipses and have to choose those ellipses in such a way that the light focuses at a point right here that we prescribe. And so this is done like that, and use the quasi-Newton method, and it optimizes it in this way. And then you can do it with, you find a design so that the same design not only focuses light, but focuses different colors at different points. So red, green, and blue, for example, this exact same design, when you send light of different colors, gets focused at different points. So this is the basic element for a camera. And so the red, green, and blue, so you can process light in this fashion. And so this is, okay, so this is the same design that's focused lights at three different prescribed points. And here is a objective function that we optimize to do that. And we can do this in 3 dimensions. And here is something focusing light at a single point. And this is a relatively small array. And you can see that you can focus light like at the middle, or you can focus the light at the corner in the domain. And so the optimization automatically generates the right arrays. Here is one where we want to optimize so that we get focusing at various points depending on wavelength and polarization. So if you're in X or Y polarization, so you go to either this point or this point, but that depends on whether it's 750 or 600 nanometer light. And so those are the two, and similarly with Y polarization. And so this is the optimized structure that we obtained. Here is a domain that has many nanoposts, 20,000 nanoposts. And so this focuses light at one point or the other. And this is a very large problem, and run in a 40-minute run in 33 nodes of 24 cores each. And this is with the FFT-based method, okay? But here is something we were reaching a point where we wanted to do this. This is about 20,000 nanoposts, you know, it's I don't know, something like 100 by 100 by 2, something like that, you know, 2 layers of 100 by 100. And that would be at one wavelength of a micron, that would be 1/10 of a millimeter. So these guys want to go into centimeter sizes. So we have to do problems that are much, much, much larger. And we saw that the FFT method was giving out, because this is something that was becoming problematic, right? The FFT at some point just gives out, as the previous speaker was demonstrating. And so that caused the development of that additional acceleration method that I mentioned at the beginning. And perhaps, hopefully, we're going to be talking about that in a few minutes. Here's another one, multi-objective optimization. We want to optimize this thing. We have this structure. And so when we illuminate it with one color light, we wanted to read the word DARPA to keep the sponsor happy. And then when we illuminate it in a different color, we get this to spell the word CAT, California Institute of Technology. And so we have these layers, and I'm going to show you the layers in a minute, but these layers do just that. And they were optimized by using gradient descent, and they were originally optimized using a dipole approximation to accelerate the optimization process. And then there was a subsequent step where the full solutions were used. You have the 6 layers. They don't spell anything if you look at them, CAT or DARPA, but if you combine them and you use the right wavelengths, then you get the word DARPA or the word CAT. I cover my first topic, and so I talk about large engineered structures and device optimization. Now, I'd like to talk about time domain solver, how you can use the frequency domain solvers to do time domain dependence. And I'm going to be talking about problems of scattering by surfaces, acoustic scattering in this case by surfaces, but the same kind of thing can be done for volumetric problems where there is volumetric variations. And although that hasn't been done, but there's a student that's starting to work on that particular topic. Okay, so we have, again, the wave equation now, and we have a scatterer, and we're going to do this try to do this by Fourier transformation, right? So these two things are equivalent in some way, and the equivalence is the Fourier transform, and we all know that, and that's why we do this frequency domain thing, because there are actual physical configurations that live in this domain, that you have a single frequency or a bunch of frequencies. Right? But we're going to use that to solve time domain problems such as this ones, right? I mean, where there is not a frequency thing anymore. And so how do we perform that Fourier transform? So we know that this is something that you could do, but it's not something, I mean, it's something theoretical. You learn it in school and then you never do it because, it is not done, right? I mean, people have done it, but there is very, very, very few references. I have this example that we unearthed from year 2000, and I don't know that it was continued this work. We looked and we didn't find anything. Is you just do the full Fourier transform of this thing, and assuming that the field has compact support, and the incident field has got compact support. So if you do this, as time grows, look at this here. As time grows, these integrals become more and more oscillatory. So you need more and more frequencies to resolve this integral. Because as time grows, this becomes more oscillatory, and therefore you need more frequencies to compute the integral. And so what that means is that you need finer discretizations, so you need more frequency domain solutions. The cost grows quadratically with time, which is very damning because, it's FDTD, each time step costs you the same amount. It doesn't cost you more. But this one, we do more time steps and it costs you more and more. And so this is challenging. And so people have remained and stayed with very small propagation domains. There is another alternative, which is it's actually it's been very, very active, and this the convolution quadrature, where this is different. So there is a preliminary discretization of the time variable by using some sort of a finite difference method, and it has to be chosen correctly so that you maintain stability. And so you have now a time domain discretization, a discrete time version of the time domain wave equation, and then that is sort of Laplace transformed, but because it's a discrete version, it's not really a Laplace transform, it's a Z transform, but it's like a Laplace transform. And you come up with frequency domain equation for a modified Helmholtz equation with a negative coefficient there, but it's also a Helmholtz equation. And so this is something introduced by Lubbock many years ago, and Banjay. And so this thing has, again, an infinite tail that becomes larger and larger as time passes. It does have dispersion errors. The frequency domain Fourier transform method doesn't have dispersion errors because there is no time differencing or space differencing anywhere. There's no finite differences anywhere. There's no dispersion. But here there is, because one of the things, the first thing we do is in this convolution quadrature is to discretize time. So in finite differences. So there are dispersion errors. And there is a nice paper by Timo Betke that analyzes various things in this and how you do the Laplace transform and how you go into complex domain. I don't have time to go into these details, but more or less these things are studied and analyzed. And so basically there are concerns that are sort of decoded into these words here. The memory costs grow with time. There's an infinite tail and so forth. And so I'm going to propose something that does a Fourier transform, and the overall cost is linear in time. There is negligible time domain numerical dispersion. There is natural parallelism, of course, for the frequency domain solutions, but there's also natural parallelism in time. So you can solve a problem in time and solve for the future before you solve for the past, or solve for the future and the past at the same time. And so you can time leap. If you want the solution at a very long time, you don't have to solve the solution all the intermediate times. You can just leap into the time that you want. And so you have order 1 cost for solution sampled at arbitrary large times, at any time you want. So you don't have to use absorbent boundary conditions of PML or anything, and you have high order accuracy. I'd like to give you some details of this. Basically, so here is the window again, that window that I mentioned that we use as part of the problem for waveguides. Here we use it for a different purpose. We take a time domain signal, a long time domain signal, and like this one here, and we window it, and we use a partition of unity so that, you know, we have many windows, potentially, as many as you want, but the sum of all the windows is equal to 1. The sum of all the windows is equal to 1. So when you take an incident field, you window this, and then you window it again and again and again. And when you sum all the windowed things, you get exactly the incident field, because the partition of unity is just that. The sum of the windows is equal to 1. So, so you have to solve for only one time then. And so when you want to compute a Fourier transform, you just have to compute this thing over one window. And but you still have the same problem that I mentioned before. As time grows, that's right. As time grows, so this integral here, you have various frequencies, and for large times, this becomes very oscillatory. And so, but because this is localized with this window, so you can localize this time to a region around a time step, the center of the window that we use in TK in this case, okay? And you can take that factor out of the integral. And so here, this becomes t minus tk, and it's integrated between minus h and h. And so the times that you have to integrate are very small. And so this exponential doesn't oscillate very much. And so we control the oscillation problem, which you couldn't have done if you had all the signal at the same time. You couldn't have done that. And so you use then, so you have to discretize each frequency and go to the frequency domain for each window. But now all the problems for all the windows are all the same, because there are something that goes between the individual minus h. So the frequency domain problems are exactly the same for all windows. And so you solve a single set of frequency domain problems at the beginning, and then you do time domain problems subsequently. And all the frequency domain problems are, of course, embarrassingly parallel. You can solve each frequency domain problem in one processor or group of processors, and each one of them can be internally parallelized. And so that can be done. And so when you do these integrals here, we use a trick. This thing is something that is windowed, so it vanishes. So this u, which is a windowed thing, you can think of it as a periodic function. Because it's windowed, just like the previous speaker did. And so you have this window function. You can expand it in Fourier series. And so you put a Fourier series inside this Fourier transform. And when you put the Fourier series, which is a truncated Fourier series, you reduce the problem to something that looks like a convolution, but it's not quite a convolution. It is a scale convolution. This beta number is not 1. If this was equal to 1, then this would be a convolution, but it isn't equal to 1, so it isn't a convolution. It's called a scale convolution, something that previously people have worked on and have developed a way to do it using Fourier transforms. It's called, so it's FFT accelerated, uses fast Fourier transforms, but uses fast Fourier transform to do this thing called the fractional Fourier transform. Okay, so the cost of a fractional Fourier transform is about 4 fast Fourier transforms, and using the fractional Fourier transform, you can do these scale convolutions like so. And so that's the way we compute these integrals. And that's it. Yeah, so we went to the frequency domain. We had the high frequency integrals. We brought them back because of the windowing. You could bring it back to low frequency regions. And so now we solve a finite number, a small number of frequency domain problems, and those we work them out. And so these are the various windows. So you operate on the various windows like so, and you have and each one is active for a certain amount of time, and you can apply that to various geometries. And I'd like to demonstrate that. Here I have this array of spheres. I like this one because this is one where there's supposed to be multiple scattering anyway. So this is a famous problem in the theoretical literature for the problem. And so you can do that for a realistic geometry, like I was showing before. You take this airplane, you can do frequency domain solutions like the ones that I was showing you earlier, but then you take many of these frequency domain solutions, and then you get a time domain solution that looks like this. And this doesn't have to, here I'm showing just one window, just one little thing, but this doesn't have to be a short thing here. Here, this is a long, long movie. And if you look at the mouse here, I'm pausing, this is a super long movie that I'm just going further and further out. I mean, this takes several minutes to watch it all. And it has various pitches, and the wavelength becomes smaller and shorter, and it does that over a long period of time, a simulation. So the overall simulation for everything that we did there took 81 minutes in 2 12-core Intel Xeon CPUs. So 24 cores, and it took 81 minutes. So out of the 81 minutes, 38 minutes was the pre-computation of the integral equation solutions and setup. And so this is the amount. There was some evaluations that require 11 minutes. But then once you get this, to solve the movie, as long as you want, that movie took 140 seconds. So if you watch the movie, I think I have it here. So the full movie that I sort of skipped was a 3-minute field movie, and it took 140 seconds. And if you just come up with another incident field that is in the same range of frequencies, then the 140 seconds, so it's faster to run it than to watch it, basically. And so you can do a very, very long incident field. And this is not in preparation. This has appeared already, and so sorry about that. So we have some comparisons here with other methods. Here I have the a convolution quadrature method and an integral equation method that I didn't mention what that is. It's a time domain integral equation method that people also use, and this is a recent version of it by various authors. And so so here is this one here is the convolution quadrature method compared to our approach, our hybrid method. And so comparable accuracy or better in our case, but it runs in a time that is 10 times smaller and with an amount of memory that is 50 times smaller or 40 times smaller, something like that. And this is for this signal that was provided in that paper, for this little tiny signal that goes up and down, up and down. So the memory here in the convolution quadrature grows proportionally to that. And so if you had a long signal, this will grow and grow and grow. And the same thing is true for the integral equation method. But for our method, it wouldn't. So the advantage is significant. But even for a small pulse like this, for a short pulse like this, even for that, there is this huge difference in computing time and memory requirement. The comparison with the integral equation method is similar. Here, the authors have provided a solution with an accuracy 10⁻⁷, so we matched it. And so the wall time was 101 minutes, and a comparable machine, and in our case was 4.1 minutes. If you want to look at this, this is in the published version of our paper, and these comparisons are there, so you can take a look at that. Okay, so you can use this in other ways. It can be volumetric. And here, for example, I'm showing something for dispersive media, where you have in the time domain a convolution here, but it's ideal for this case, and so you can go to the frequency domain and solve these problems easily, and then you go back to the time domain using this approach. And here is this is an experimental paper where you have castor oil propagation in castor oil between 2 points, and so if you look at how the signal propagates, then as it moves in, it gets damped. And so here this is an insignificant amount of time in a single core, and it gets the solution just right. And of course it should, because it's a very simple thing. So here is a cavity problem where the field comes in, and then this is in 2 dimensions. You can do this in 2 dimensions too. There is some impact of the Huygens principle that is not valid in 2 dimensions, but we took care of that. I don't have time to look at the details of what that is, but the Huygens principle is an issue. It can be resolved, and we did resolve it. And this is a paper is in preparation, but it's an archive version of it that is already available. What if you have closed cavities? When you have a closed cavity like this, the interior of this domain, right? So perhaps the interior of this domain is an interior domain, and there you cannot solve the frequency domain equations because there is no uniqueness at some cases. But we did that by just splitting the domain in 2 regions and looking at this as a multiple scattering problem where you solve one first and you get the field here, you record it on this one, but that is not what you want. So then you do it again to correct that one, and you get it wrong on the other side, and you correct back and forth. And so you bootstrap yourself and you progress in time in this fashion. And in that way you can solve interior problems as well, like this one here. And so this is something in preparation in collaboration with Tao Yin. Okay, so this is time domain from frequency domain. And before I talked about frequency domain accelerated solvers, so I think I still have a few minutes. I'd like to talk about this frequency domain methods. I think I started a little bit after exactly the hour. So perhaps I have a few minutes to talk about this novel method.
Yes, sure, go ahead. You have about 8 minutes or something like that.
Okay, great, thank you. So all of these problems require massive amounts of frequency domain solutions, and some of them are high frequency domain solutions that are expensive to solve, and we do it using fast Fourier transform methods, but at some point we saw that we could do it. We did it in parallel, but I mean we were not going to do like 30,000 cores with that. I mean it becomes. The fast Fourier transform becomes a problem, becomes this load that you have on your back, and so you had to get rid of it, find a way. So we had to think about, is there some way that we can do an acceleration with that fast Fourier transforms? Of course, there is other methods that you can use. You don't have to use these equivalent sources, this fast multiple method, right? But all of these methods use fast Fourier transforms. This is an essential thing. Right, so you have this fast Fourier transform in the FMM, where you have, for example, in some versions of the FMM, you have the spherical the spherical wave expansions, and so you have these spherical wave expansions that have to be translated to another point, and to do that, people use a fast Fourier transform. And there's other versions, the fast directional domain algorithm that doesn't use spherical expansions, but they use linear algebra, but that also use an FFT at some point. All of these methods use a fast Fourier transform. So I have a few quotes here. So clearly there's the impact of FFT in the FFTs, methods like the one I described, but there is also in the FMM. So references 1 and 2, Enquist and Ying, and Ying's and George's virus, he's here. The top part of the FMM is a bottleneck. Reference 3, parallelization is a bottleneck, the part of the FMM relying on FFT, as it suffers from lowest arithmetic intensity and likely suffering from bandwidth contention. And then reference 4 says that there's an alternative to using the FFT, but then it discards it because it's less efficient than the FFT-based procedure. And so, anyway, so there's a history of this, and as far as I know, and I look hard, all these methods use FFT in some way, shape, or form. So what I'm going to show you now is another method, the Ifgf, Interpolated Factor Green Function method, and that method doesn't use FFTs. It's a new integral acceleration paradigm. It's applicable to general smooth and non-smooth kernels. I'm going to do it for this kernel here, but you could use the Laplace kernel or the Stokes kernel or any kernel. A smooth kernel, just the exponential with any phase that you want having. It doesn't have to have absolute value, fast, very low memory requirement, much lower than the FFT-based methods, and especially in the FMM. It can be parallelized efficiently. And it doesn't use FFTs. That's the main thing. It's n log n compute cost. It's extremely simple. It's trivial. It's trivial. Okay, you could go home and program a simple version of it this afternoon. And it does not utilize FFTs or special function expansions or translation operators or high dimensional factorizations or equivalent sources or parabolic scaling. It doesn't use any of the elements that these acceleration elements that were previously used. And I'll try to demonstrate this. It's going to be quick because I don't have a lot of time. But what I'm going to do is this. I'm going to take this little square here, and I'm going to put a point source at that point, okay, of a certain frequency. And then I'm going to do an example. I'm going to look at the green function for that problem, the green function of the point, that's the point source. And I'm going to look at the field that it generates, the field. I'm going to plot the green function, basically. Plot this as a function of x along this line. And if I do that, I get these oscillations that I have here. And I do that for h. So, and if I do this for this point, this is the worst point in the box. If I put it in the middle or anywhere, I'm going to get a picture that is just like this. So this is an example, but any point inside that box will be the same. And notice that I'm 1 box away. I'm starting this 1 box away. And so I do that plot starting 1 box away along this line and along this x. And so I get these oscillatory things. For h equals 0.1 lambda, I get this blue curve. For 0.5 lambda, I get the red curve that oscillates a bit more. For h equals lambda, I get this yellow curve that oscillates more, and then the purple line for 2 lambda. Okay? And what I'm going to tell you now is the crux of the method. This is it. This is the main idea in it, is that we're going to look at this green function, and we're going to factor the center green function. When you do that, then there is an x that comes here and an r and like that. And so this can be re-expressed in this fashion, right? Where you get e to the I kx over x is one thing times this other thing. And this other thing is gs of x and x prime. We took that away. Here is what this is. And we call that the analytic factor. And this, we call it the analytic factor. This is the center factor. This is the center factor because it's centered. And this is the analytic factor because it's analytic all the way up to and including infinity. This is an analytic function at infinity in the sense of complex variables. All right, so it's defined at infinity. This one obviously isn't analytic at infinity. It oscillates all the way to infinity. That's an essential singularity at infinity. But this one is analytic at infinity. And you can check that, and I'll say something about that. But the consequence of that is that when I do this plot, if I take the same example here for h equals 0.1 lambda, I get something that is essentially constant. And if I take 0.5 lambda, is the red one, that is also essentially constant. And if I take lambda, which is this, and it's also essentially constant. And if I take h equals 2 lambda, the largest one that I had here, that was pretty oscillatory, is also essentially constant. And then I can do more, 5 lambda, 10 lambda, 20 lambda. And this eventually is essentially constant at infinity because it's analytic at infinity. That's what it has to be. And so because it's so slowly oscillatory, I can interpolate this function. And I cannot interpolate just this one. If I have not one source, but a million sources in here, I can interpolate the combination of them. And that is what the method is about. You just, in order to evaluate a million sources that you may have in here at various points, you don't have to evaluate the million sources at all the points. You can evaluate the million sources just at a few points and then interpolate. And once you've interpolated, you multiply by the center factor. That is the idea of the acceleration method. So here is what this is describing. And so this is, you multiply by the center factor at the end. It's the common factor of all of them. And then, so you have to sum these things, and to interpolate this is a slowly varying thing, and you can do this by interpolation. And here are the interpolation stencils that we use. And so you just use a few points here, and you can interpolate at other points of the surface. So if you do this, it's still too expensive. You've saved quite a bit by doing this, but it's still too expensive because it's still n-squared operations to do it. And so what we're going to have to do is to do this repetitively. And so here is what it is. So say that you have a square right here, this box B421 here. OK, so that box, I said that the interpolation has to be done one box away, right? So I cannot do the interpolation at any of these points. I cannot do it at any of these points. I can do interpolation to everything else, right? But I'm not going to do it to everything else, because if I look at the parent box for this thing, right? So the parent box will be able to do that when this one of its size of boxes away, right? So it could be able to do it at this box. I could do it with a parent box. So here at this one, I only have to do it for the ones that the parent box cannot do. And those are the ones that are neighboring it. And so for this one, I do the interpolation onto these ones, and also onto the interpolation points of my parent box. And then I keep down, I bootstrap that in, and I propagate that to all over the surface. So interpolate onto the nearest neighbors and onto the interpolation points of my parent. And so there is some theory that says how you do this. This is the reason why this is an analytic factor. This here, when you do this factorization, you see that this has length 1. This is length smaller than 1. So this is analytic all the way up to infinity. And you have 1 over s here. You can figure it out. This is trivially analytic all the way up to infinity. And so this is the error analysis of the interpolation. The error comes out to, so we have this theorem here that says that the growth is for kh bigger than 1 is like kh to the n for the nth derivative, and is for kh less than 1, this is just bounded. And so if you look at the error analysis, then that means that the error of interpolation is less than kh delta in the radial direction to the power. So what this means is that when you increase the box size by a factor of 2, you have to decrease the interpolation interval by a factor of 2. So the box is larger, the interpolation interval becomes narrower. And so this is what it is, and that keeps the cost constant. And all this, you put it all together, this amounts to n log n operations. This view graph here means that the interpolation, the way I indicated before, is the right way to do it. If you miss the exponential term, it doesn't work. If you means the 1 over r term, it doesn't work. So the one that works perfectly is this one where we incorporate all the pieces in it. And so you get an error that is constant. And so also you have to interpolate in the variable in which this is analytic at infinity. Not only you have to use the factorization, but you also have to use that variable to interpolate. And this is this variable s, which is h over r, which is 1 over r, which is the variable in which this is analytic at infinity, at s equal to 0. R equals infinity is equal to s equal to 0. So this error remains constant across levels as the cost is optimized. And this is a scheme, n log n operations, because each time you do order n operations at each level, and you have log n levels, and that's all n log n operations. Here is the code. Here's the total code. Is nothing to it. So these two things are the same, basically. I mean, interpolate, and that's it. So this is a Laplace solution in 3 gigabytes of memory, 6 million unknowns, 5 digits of accuracy. This would have took 305 minutes in a single core. This is a single core. And it would have taken 13 days to do directly in the same machine. And so we have here something that goes up to 128 wavelengths in size. And it takes 40 minutes in a single core. 10 gigabytes of memory, 5 gigabytes of memory for a sphere of various radii. Here we have an ellipsoid of size 512 wavelengths in one dimension, in one of the dimensions, and this is 10 gigabytes in a single core. And here comes, this is something we're doing right now. This is absolutely unpublished. We're working on it right now. And there is many things we didn't do. This doesn't include adaptivity, for example. There are boxes that can contain 1 point, and there is nothing we do about it, okay, so far. So we need to look at the details of this. But even then, the scaling is pretty good. I mean, this thing up to from 28 to 448 cores, it gets for the sphere 90% efficiency. And so there is room to improve, this huge room for improvement here. We're going to do this in GPUs. I mean, this is really well adapted to GPUs. I think we can go to very large machines now using this and try to do some of the problems that we have to do those designs at the macroscopic levels for photonic devices and time domain solvers for other problems. So these are the properties that I mentioned before. It's n log n. It doesn't use FFTs. It's extremely simple. It can be efficiently parallelized because it doesn't use FFTs. So these are the topics that I cover. I think I'm in time. And so I talked about frequency domain accelerated solvers for real engineering structures and aircraft and submarines, and Maxwell equations and acoustic equations. You could do other equations. You could do Stokes equations as well. The high order methods are well suited for doing that. Then using frequency domain solutions, I talk about how to do time domain solvers by doing Fourier transforms, windowed and fractional Fourier transforms. And then I mentioned this novel frequency domain acceleration, which scales well because it doesn't use fast Fourier transforms. So that's all I have, and thank you for your attention.